How does the motor cortex control neuroprosthetic devices? Imagine being able to move a robotic arm just by thinking about it. That's the power of the motor cortex in controlling neuroprosthetic devices. The motor cortex is a part of the brain that plans and controls voluntary movements. When you decide to pick up a cup or wave hello, this area sends signals to your muscles. In neurotechnology, scientists tap into this process to help people who can't move normally. Neuroprosthetic devices work by listening to the electrical signals from neurons in the motor cortex. Tiny electrodes, often about the size of a grain of rice, are implanted directly into this brain region. These electrodes pick up the signals when a person thinks about moving a limb or performing an action. The signals are very faint but contain important information about the intended movement. Once the signals are recorded, they are sent to a computer system. This system uses special algorithms to interpret the neural patterns. These algorithms translate the electrical signals into commands that tell a robotic arm to open or close, or a computer cursor to move across the screen. The process is quick, often happening in just milliseconds, so the user feels like they are controlling the device naturally. A key part of this process is neural adaptation. When someone first starts using a neuroprosthetic, their brain needs time to learn how to generate the right signals. Over weeks or months, the brain forms a stable neural map for controlling the device. This map is like a mental blueprint that helps the person recall how to operate the prosthetic smoothly. The more consistent the decoding algorithms are, the easier it is for the brain to maintain this control. It's important to remember that the motor cortex doesn't work alone. Other parts of the brain, like the cerebellum, help coordinate and refine movements. If the cerebellum's activity is disrupted, it can make controlling the device less accurate. This shows how many parts of the brain work together to support neuroprosthetic control. People with paralysis or neurological disorders can use these devices to regain independence. They can operate robotic arms, control wheelchairs, or even type messages on a computer. The technology is constantly improving, with research focusing on making signals more accurate, increasing the range of movements, and adding sensory feedback so users feel more connected to their devices. In essence, the motor cortex controls neuroprosthetic devices by generating neural signals that are recorded, decoded, and turned into actions. The brain learns to adapt from stable control patterns, making these devices more reliable and intuitive. This progress is opening new doors for restoring movement and communication for many individuals.